me start recording the lectures. And so I guess I posted in your WhatsApp group a nice image which can have all these planets. So let me see whether I can pull out that image, which will give you a right, not actually yeah, right here. So let me share this with you as well. So these are something, apart from the lectures. I mean, this is how astronomy works. I mean, you don't, I mean, we can't go only with the textbooks and things because the sky keep changing. So we have to discuss what you can see up in the sky, right? So I assume that you can see my screen, and this is the actual positioning of all the planets, right? And there are some other, minor planets as well. You can see the Mercury, Venus, and actually very close to the moon, you should see Uranus if you have a smaller telescope, right? So this is how it was looked like June 24th morning. So that should be, I mean, yesterday morning, but I mean, you should be able to see all these planets again in the next few days as well. And then you have the moon. You can see it's a crescent moon, and then as and Jupiter is always larger, so that's why you can see it as a bright object. And between Jupiter and Saturn, you should be able to see Neptune, and you can see that what I have mentioned here is Neptune and Uranus is not in the order that we discussed earlier, but they are also visible, right? Basically, I would say that this is one of the rare occasions that you can see all the planets in the sky if you have a small telescope, right? So that's why we are discussing this a little bit in more detail, right? Right, having that in the mind, and let me just go with our lectures today. So stop sharing. And by the way, if any of you have any questions regarding these things, you feel free to ask, right? So I will try to answer as much as possible. And so let's go into the regular lecture. So I will go a little bit beyond 1 hour limit today, maybe up to 1.5 hours, just to cover what we have missed, but it depends on the status of the lecture, right? So if there is an endpoint of the lesson, I will stop from there. So that's how it works, right? I have it here, and then lesson. Right. So I assume that you should be able to hear me right now, right? So thank you for having the message. Just confirm me now whether you can hear me or not, right? So I assume that you can hear me now. Right. Thank you. So let me start the lesson then, since we are running out of time. And today's lesson, we are moving on to the next chapter. So we basically talked about the history of astronomy and how some of these concepts like the size of the earth and distance to the earth and some of these constellations were observed by ancient astronomers, and how they deduce things, the various things about the sky and those kind of things. And then after that we talked about uh, retrograde motion and how ancient astronomers tried to explain the retrograde motion, and at the same time how these heliocentric model and geocentered model about our solar system was introduced and then explained by different philosophers and astronomers. And that's what we have learned up to now. And then we moved into the modern astronomy a little bit, how the modern astronomy started and those kind of information. And I guess how we basically how Galileo used his telescope for observations, those kind of things. Now today what we are going to discuss here is uh, basics about the orbits and gravity. So which means this is some will be connected to physics, some of the physics concepts as well, how the orbit of a planet can be explained, and how gravity works and how it is applied to explain different phenomena like the motion of planets and motion of satellites, spacecraft, those kind of things in astronomy, right? So that is our aim for today's class. And let me now this image, right, you see here on the screen, and I assume that all of you can see my screen. And this is an image of International Space Station, right? So which will orbit once every 90 minutes. So which means it will complete an orbit around the Earth for every 90 minutes, right? And just some additional information, if you want to uh, see where the space station is right now, there is an app, right? For this International Space Station, you can download it and then look for the position of the International Space Station. And there are, when it orbit around the Earth, there are instances in certain days that ISS goes above our country, right? So if you locate that location and the time from the app, you can go outside and look at the International Space Station, right? And this is sometimes, people used to comment that there is an object and like unidentified object moving through the sky in some days. But if you look at the location of the International Space Station on that particular day, you will see that most probably this is the ISS just going uh, above our country, right? So that you can see it easily, right? So the reason that I have this particular image here is we are going to talk about how these space stations are positioned on the orbit and how it moves around our Earth, right? Not only this International Space Station, but also about the planets and minor planets, asteroids, those kind of things, right? Now the question that you should have is, now at the beginning I have explained you that there are like 8 planets in our solar system, And if you go outside and look at the sky from your naked eye, you can see 5 of those planets easily, and it will be 6 including our Earth. So there are, except the last 2 planets, you can see all the planets up in the sky. Now, the question that you should have is, how would you find a new planet at the outskirts of our solar system that is too dim to be seen with the unaided eye? Now, the best example is Uranus and Neptune, right? As you can see, they are up in the sky in these days, but you cannot observe them from your naked eye. So there should be a way or a method that we can detect these dim planets, right? So because their brightness is not that much. Now, actually, this is a complex problem, right? To these, most of the time, these dim planets are in the outskirts of our solar system, which is very far from us, and there is no way that we can observe those from our naked eye. And because of that, we should have a mechanism to, detect these kind of planets, right? Now, this is why the science is here, right? Now, as a complex problem, you need better observations and better models of our planetary system to observe and detect these kind of planets, right? So we have to have better observations, and there should be better models to detect these kind of planets. Now, to make these models, you need a lot of physics, right? So that's why we discuss about these different theories and theorems and equations. Now, if I go back to 1550s, like, let's say, like 500 years ago, there was an astronomer called Tycho Brahe, and you probably have heard about him. And in this picture right here is a picture of him and also his instrument, where which he used to measure the angles, right? So what this instrument did was that he was able to measure the altitude of celestial objects. So that means how high a particular object in the sky he was able to measure from his instrument, right? Now, what you see here as this large curved instrument right here is the one that he used to measure these angles, right? And on the right hand side is the other famous scientist, which we called as Johannes Kepler, right? So he is very famous, and probably you know why is that he has introduced these laws that describe the motion of planets, right? And I guess you probably have learned about this in your A-level physics classes, and maybe in within first 2 years of physics in your university. So I am going to explain these laws very briefly, and then we are going to use these Kepler's laws, to derive different things about our planets. And let's see what we can do with his Kepler's laws. Right. Now, before we go into that, there is a nice connection between Tycho Brahe and Johannes Kepler. Right? Now, you can see that Brahe lived from 1546 to 1601, and Kepler lived from 1571 to 1630. And you can obviously see that Johannes Kepler came after Tycho Brahe, but not much difference here with their, lifespan, right? And actually, Kepler worked under Brahe for some time. And what Tycho Brahe did was he made continuous record of the positions of the sun and moon and their planets for almost 20 years. And it is this data actually which led Kepler to discover this, not actually discover, find these 3 Kepler's laws. Now, as you can see in the previous data, Brahe died in 1601, And after that, Kepler got the full possession of the priceless records from Tycho Brahe. Because when he was living, actually, he didn't give all these details to Kepler for some reason, you know. But once he died, uh, so what happened was Kepler got the possession of all the data collected by Tycho Brahe, and then he analyzed this data. And from the analysis, uh, Kepler developed some principles. Right now, these principles are the three laws that we are going to learn, and you probably have learned this in your earlier physics courses as well. Uh, Now, these laws described the behavior of the planets based on their paths through space. Basically, what these three laws means is that they explain the behavior of the planets, right? The motion of the planets, how they move on the sky. Right now, when we learn about this Kepler's planetary motion, we need to have a general idea about, you know, little bit of mathematics behind this, and probably learning or having the knowledge about conic sections, which we normally talk in mathematics, will be important, right? So that's why I have this little note here. You can see in this diagram right here, there is a cone, and you probably, I don't know whether you know about this. When you take a cone, uh, the circle, ellipse, and parabola and hyperbola, so they are all formed by the intersection of a plane with the cone, right? And this is why these such curves are called conic sections. For example, you can see here is the cone, and cone is intersected by uh, right here. When you have an intersection of the cone and the plane in this way, in this blue color, it is called a hyperbola. And if there is an intersection like this, that is called a parabola. And this kind of intersection, you will have an ellipse. And if it is an intersection like this, which is, you know, parallel to the base of the cone, that will be a circle. So that you obviously know, right? And you can see that how the shape of these four shapes are changing based on uh, how they intersect, you know, with the cone, right? So that's the whole. That's what you have to understand here about these shapes and the conic sections, right? And when you take an object, and when it goes through, you know, the space, the path of that object we normally call as the orbit, right? So that's what we call as, you know, we talk as orbit of the sun, orbit of moon, orbit of planets, like that. When I tell orbit, that what that means is that is the path of the object through the space, right? So that's how the orbit is defined. Now, so what Kepler figured out by working with the data for mass, right? So that is the closest planet for us. What he discovered was that orbit of the planet had the shape of somewhat flattened circle or ellipse. So this is his first finding from Tycho Brahe's data. By looking at his data, he figured out that orbit of the mass is an ellipse. So the mass goes in a elliptical orbit around the sun, right? So that is one of his findings. Now, now we know that almost all the planets are going around elliptical paths, and because of that, it is important for us to learn a little bit more about this ellipse, right? What is an ellipse and what are the properties of an ellipse, because that will give you a good understanding about motion of all these planets, right? Now, when we take an ellipse, the sum of the distance from two special points inside the ellipse to any point on the ellipse is always the same, right? So that means the sum of the distance from two special points inside the ellipse to any point on the ellipse is always the same. So that means here is how you can make an ellipse. Now, if you have two tacks like this white tack right here, and if you have a string put in this way and try to make make a diagram, you can have an ellipse like this. Now, this will also tell you that uh, now let me skew this. Now, as I have mentioned here, the each tack represents a focus of the ellipse. Here is one focus and here is the other focus, right? Now, if you take a circle, there will be only one. There is a focus point only one, but that is the center of the ellipse. But there are two focus points for the ellipse, right? Because it is, not a circle. Now, if you compare this with the solar system, one of these tacks will be our sun, right? Now, this stretch string will complete one elliptical, one ellipse. And if you take a planet, the path of that planet will be this ellipse, right? So that's how it works. And now, if you go into this second image right here, the distance from here to here is called the length of the semi-major axis, right? And normally if you take the twice that length, that means the distance from here to here, that is called as the major axis of the ellipse, right? Now I have defined all these points here about the ellipse. The sum of the distance from two special points inside the ellipse to any point on the ellipse is always the same. These 2 points inside the ellipse are called its foci, a word invented for this purpose by Kepler. So what that means is sum of the distance from two special points inside the ellipse to any point on the ellipse. So that means if you take this point, if you take the sum of the distance from here to here plus here to here, that length, that distance will be equal to just give me a minute here. So I will get back to you, right? So I have an urgent call. Right, so I am back here. So what I was telling you, some of these properties about the ellipse. So what I tried to explain here is, if you look at this particular diagram, you can see that the distance from here to here and here to here will be a constant, right? So that's what I was trying to explain, because you can see that if you uh, change this point to point somewhere here, and then this distance from here to here will be smaller and this will become larger. However, the addition will not change because you are just moving the same string from here to here, right? So it will reduce the string, the distance from this side, and increase the same amount from the other side. So that means if you take any point on the ellipse, the distance to the addition of the distance to the two focus will be a constant. So that is a property that we have for the ellipse, right? And the special case will come into play when you go into this end or that end, right? So these are called semi-major axis. And so if I go into the next slide, so I have uh, explained all these properties here. The sum of the distance from two special points inside the ellipse to any point on the ellipse is always the same. So that's what I have described. And these 2 points inside the ellipse are called its foci. So that's a plural word for the focus. And the other thing is the ratio of the distance between the foci to the length of the semi-major axis is called eccentricity. And I'm not going to explain this. You know what eccentricity means, right? So in general, what that means is how circular it is. So if it is completely a circle, so the eccentricity will be 0 because the ratio of those two lengths will be 0, right? And the widest diameter of the ellipse is called its major axis. So that is this diameter from here to here. So that's the widest one. So that is called the major axis. And the other one, which is the lowest diameter, that is called the minor axis for the ellipse, right? So these are actually not directly related to the astronomy, but it is important that you know these highlighted terms when we talk about the motion of the planets. And now if you get an example, let's say for the orbit of the Mars, the semi-major axis of the orbit of the Mars, which is also the planet's average distance from the sun, is 228 million kilometers. Now from the sun to the Mars, it's the semi-major axis length will be 228 kilometers. That means if I go back to this particular diagram right here, the major axis is from here to here for the ellipse, and the semi-major axis is half of that. So that means from here to here. So that is the half of the distance. And if sun is right here, and if this is the orbit of the Mars, the distance from here to here is that distance, 228 million kilometers, right? And if you look at the average distance from the sun to the Mars, that is also equal approximately to 228 million kilometers. Now, this is a special case. This happens when the orbit of the planet is nearly circular, right? You can, I guess you can understand it. And the distance is 228 million kilometers. Now, we can see that it is true for the case of Mars because when Kepler was using Bryce data, he found that the Mars has an elliptical orbit with sun at one focus, but the eccentricity of the orbit of the Mars is only about 0.1. So that is the ratio between the major axis and the minor axis. If that ratio is very small like this, so that means you have approximately the same distance for the major axis and the minor axis. So what that means is it is a nearly circular orbit, right? That difference is smaller. Right? Now later, Kepler generalized this particular result as his first law of planetary motion. So that means the orbits of all the planets are ellipses. So remember that is the first law that Kepler introduced, right? The orbits of all the planets are ellipses. And not only that, and he moved on to the second law, which tells you, or we call that this as the law of equal areas. And the idea is, if you look at this particular diagram right here, you can see that the sun is right here in one of the foci in the planetary system, and let's say there is a planet that moves around this particular orbit. This is an elliptical orbit that is represented from blue color. And if you have the planet right here at number 1 position on the right hand side, then let's assume that this planet move from here to here, number 2 position, right? Now let's say the time it takes to move from here to here is simple t, right? And if you go to the other side, let's say the planet moved from number 3 position to number 4 position during its travel around the sun. It will take only this the same amount of time t, right, to move from number 3 position to number 4 position. Now what you can understand here is this point, the point on the right hand side, when it go from number 1 to number 2, this side of the orbit is very close to the sun, right? And because of that, it has to go a larger distance. Like when you go from 1 to 2, it has to go to a larger distance. So which means it has to travel a little bit faster, right? Assuming that these two values t and t are similar, right? So which means from here, when you go to the left hand side, it has to go from here to here, from number 3 to number 4. You can clearly see that it's a smaller distance, so it will take again the same time, so it will be slower when it go from here to here. And you can obviously understand why it is, because this is closer by, so the object will move faster, right? So the Kepler introduced a second law based on this concept. So what he has mentioned here is that the planets speeds up as it come closer to the sun and slow down as it pulls away from the sun, right? So that's what I have explained to you. When the planet is closer to the sun in this right hand side, the planet will speed up its motion, so it will move faster. But when it is far away from the sun, it will move slower. Now that is why to go from 1 to 2 on the right hand side, it will take a time of t, and the same time will take to move for the planets to move from number 3 to number 4, right? Now as a result of this, Kepler found that in equal intervals of time, the areas swept out in the space by these imaginary lines are always equal. So what that means is at equal times, they will sweep out equal areas, right, on the space. And you can clearly see that in within the time period t, it has swept this particular area, which I have denoted as B. And within the same time, it has swept out the area that I have denoted here as A. Now you can see that even though the arc length is smaller here, the area is larger, right? Because the sun is far away from this particular point. But on the other side, the arc length is larger, but the distance to the sun is smaller. So that's why this particular area will be similar to this particular area. So Kepler introduced this as his second law, which we call as law of equal areas. So his idea was that in equal intervals of time, these planets will swept out equal areas, right? So that is the idea. So I hope you understood what this means. And Then let's move on to the Kepler's third law, which is the law that we mostly used for different type of calculations. Now in 1619, Kepler discovers the relationship that relates the planet's orbit to their relative distance from the sun. So this is why Kepler's third law is important. You probably have learned it before, but we have to apply it here. So we need to understand what the law means, right? So he tried to derive this relationship uh, that is about the planet's orbit and the distance from the sun, right? Now let's see, we define the orbital period of a planet. So that means the time it will take to complete one orbit as P. So the planet's orbital period will be P, and this is important, right? The next one is, let's define the semi-major axis of the planet as A. Now, by having the knowledge about the ellipse and different points on the ellipse, I hope you can understand what semi-major axis means. So let's say the planet's semi-major axis is A, right? So that is basically the average distance from the sun, right? Now, what Kepler's third law tells us is there is a relation between this orbital period and the semi-major axis length, and that relationship is the square of the period is proportional to the third power of the semi-major axis length. So we call this as p squared proportional to the a to the power 3. Right? So this is called the Kepler's third law. And remember, as students who are following astronomy, you have to remember it, right? You will be checked whether you remember this particular law, not only just the equations, but you should know what each of these terms means in the equation and what kind of units that you can use for this particular equation, right? So that is the important part in astronomy. You don't have to derive this, right, in this particular course, but you should know how to use this particular law. And let me show how the units works here. Now, I showed you that p squared is proportional to the a to the power 3 in the previous slide. However, if you measure the orbital period in terms of years and a, which is the length of the semi-major axis, in terms of astronomical unit. Astronomical unit is a unit actually we use to measure distances in astronomy, and this is defined as the average distance from Earth to Sun. So that is the distance from our Earth to the Sun will be one astronomical unit, right? Based on that, you can convert the other units. Now, if you use these two types of units, the two sides of the formula that we discussed earlier is not only proportional, but also equal to each other, right? Now, this is very important for you to remember, right? Because I have the experience in exams when I used to give some problem, students try to do a lot of complex things to, convert the units. And so that will make the problem even more complex if you try to convert the units, right? You have to be very careful with the units when you are, when you take or try to learn about astronomy, because if you convert the units, that is not necessary to do, and then your problem and the calculation will become uh, more complex, right? So that is something I think you should avoid actually. And now, if you remember that this is very important once again, if P, which is the orbital period, is measured in years, and if the A, which is the length of the semi-major axis, measured in astronomical units, you can directly tell that P is P squared equal to A to the power 3, right? So that is important. Now, this Kepler's third law applies to all objects orbiting the sun, including Earth, right? So you can basically apply not only for planets, for minor planets, asteroids, comets, anything you can apply this, right? In any object that is orbiting around the sun, Kepler's law will be applicable, not only for the planets. Right, so I'm giving you an example or a problem here. So remember, you can note down this equation if you need. P squared equal a to the power 3. And my question is, imagine an object is traveling around the sun. What would be the orbital period of the object if its orbit has a semi-major axis of 50 astronomical unit, right? Now remember the units and the Kepler's third law and try to apply that to find the orbital period of this particular object. Now there is an object, let's say you become an astronomer in the future, and then you observe and find a strange object and you keep observing that, and then somehow you found that, okay, you found the orbit of this particular object, and you were able to measure the semi-major axis length somehow, and it became 50 astronomical unit, right? Now, what would be the orbital period? Then you can guess the orbital period of this particular object, right? So I will give you a few minutes. Let's say one minute. Try to answer this question, and you don't have to be exact, right? If it is a decimal place number, you can just approximate it and give me the answer, right? So let's see whether you understood what I have told here. I have one response from you, and how about the others? Right, two responses. Right, so your answers seem to lie down around 200, between 250 and close to 300, right? Maybe a little bit more than 300. And remember that the answers would come in terms of years. One has an answer 350 and there is an answer for 354. Let me, so since we do not have much time, based on these two answers, so there is another problem for you. What would be the orbital? I will discuss both problems at the same time, right? So that's why I have given the second problem. What would be the orbital period of an asteroid? So that is a rocky chunk between Mars and Jupiter, since we have not talked about asteroids until now. So they have found that the semi-major axis length of this asteroid is 3 astronomical unit. Now you need to find what would be the period of this particular object. Now remember, these are very practical problems, right? One day, if you go into work in some place, or let's say you work for NASA or somewhere like that, and then these are the first basic problems that you have to know before you go into anything complex than this. Of course, there will be something called perturbations and other effects that you have to add, but this is the basic, right? So that at the first place, you get an idea, right? Then you add all these minor corrections and everything, because so there are other effects, gravitational effects for these objects, because Asteroid is not the if you have, this is assuming that you have only the sun and the asteroid, only two body, right? But there are other objects on the sky that affect for these kind of motions. But this one, what would be the orbital period of an asteroid with semi-major axis of 3 astronomical units? So this is kind of the other version of the problem. So I'm waiting for your responses, right? Remember, this feedback is very important, because otherwise, since we are, connecting online and we don't have physical interactions, I need to make sure that you are absorbing and you understand what I am trying to teach, right? Otherwise, there is no point of doing that. So this is why I do not personally prefer that students do not join to the lectures and just try to watch the videos, because that will not work most of the time. Then I have seen that in the results in last year as well. Right, so thank you. I have one answer, like 5.2 years. So let me just go into the answers, right? So your answers are very correct. So the first one was the object is traveling around the sun. What would be the orbital period of the object if its orbit has a semi-major axis of 50 astronomical unit? Now, since we are given the length of the semi-major axis in terms of the astronomical units, we don't need to worry about that, right? So we can directly use p squared equal a to the power 3 equation. Here, I have directly calculated the p, which is the square root of a to the power 3. And if you take the values and do the calculation, that will be approximately 353.6 years, right? And you can see that how why these theorems and these findings are important for us when you do actual observations, because now for the semi-major axis length, you may be able to measure, right? But if the period of that particular object is 353 years, you will not be able to confirm it within your lifetime, because we don't live 350 years. No, normal lifetime is our maybe 60, 70 years in these days. So this is how you confirm the period. Then you can report it, and maybe somebody else at least can look at it after 350 years to see whether it works or not, right? But semi-major axis length, it's a measurement, distance measurement. You may be able to use some kind of, method to measure the distance and find it. Of course, not from a tape, but there are other methods of finding distances in astronomy. We will talk about those. And on the other hand, there is an object that you need to find the orbital period, which has a smaller semi-major axis length, right? So that is 3 astronomical units. So it's the same problem, right? There's two versions of the same problem. So we'll get 5.2 years. So your answers are correct. So at least one of you got it correct. So make sure that others understand these things. But I mean, these are the things that you will be checked, right? So once you learn a course like this, what I expect is at least you should know these basic theorems, and you can do a small calculation like this, right, as an outcome of the course. Right. Now there are two other examples, since we do not have much time to get all these answers. I have mentioned two other examples here. Probably you can go through them and see how those works, right? So the first one is using the orbital period and the semi-major axis of Venus and Earth that are provided here, calculate p squared and a to the power 3 and verify that Kepler's third law. Venus orbital period is 0.62 years and its major axis is 0.72 astronomical units. Earth's orbital period is 1 year and the semi-major axis is 1 astronomical unit. You just need to verify whether this is now this Kepler's law works or not based on this data. Right now, this is what actually Kepler did as well. When he had data, he recorded the data and looked for these relationships. Right now, even today, this is what astronomers do, because we have large volume of data that coming from different type of telescopes. We are actually in nowadays what we do is since the volume is larger, we use different data science and data analysis methods to analyze this data and look for relations. Right now, this is what exactly you have to do. Now you know the relation, you are going to verify it using this data that you have. Right, so I'm not going to go through the answer. Read through it and see whether you can understand and see whether it makes a sense, whether the Kepler's, whether these objects like Venus obey the Kepler's laws. Right, and the other one is very similar to that, using the orbital period of the semi-major axis for Saturn and Jupiter that are provided here. Calculate p squared and a to the power 3 and then verify that they obey Kepler's third law. Right, so you are given the Saturn's orbital period, that is 30 years, and the semi-major axis is 9.54 astronomical units, and for the Jupiter it will be 12 years approximately and 5 astronomical units. So you can just do the calculation and see whether these numbers agree with Kepler's third law. Right, so these are real values now. So make sure that you do the calculation and test it. I have given the answer for you to check as well, but do not look at the answer at the first place. Try to do it yourself and then see whether these calculations are right or not. Right, now to summarize what we have done up to now, we talked about the Kepler's first law, that is each planet moves around the sun in an orbital is an ellipse with the sun at one focus of the ellipse, so that we know, right, all the objects are moving in elliptical orbits. Right, so that is Kepler's first law. And the Kepler's second law is the straight line joining the planet and the sun sweeps out equal areas in space in equal intervals of time, and that is this law right here that we talked. Right, so that is the Kepler's second law. And the third one is the last one that we talked, that is the square of the planet's orbital period is directly proportional to the cube of the semi-major axis of its orbit. Right, actually the version, the Kepler's third law version that we talked up to now here, is a specific one that you have to use specific units, and this is the mostly used form of the Kepler's law in astronomy. But there are other ways of using it which you will see in the future, and this is just for your information. Now you can see that Kepler did a lot of service, a lot of work for astronomers by having these laws and other experiments. Now, as an honor of the scientist who first devised the laws that governs the motion of the planets, there was a spacecraft that is built to search for planets orbiting other stars. Right, because we now know that we knew that there are planets are moving around our star, which is the sun. But then now actually astronomers are looking for planets orbiting around other stars. So there may be other stars and there may be planets moving around those stars. Right, and these kind of planets are called exoplanets. So planets that are in the other solar system. Right, and you probably have heard this name regularly in the news sometimes, exoplanet search. Right, and actually there were some Sri Lankan scientists as well who involved in some finding some of these new planets using the data from this Kepler mission. Right, so there was a spacecraft dedicated to take data or gather data to look for these exoplanets. right? And they have named this mission as Kepler mission as an honor to Johannes Kepler, who discovered these laws of planetary motion. Uh, Now, if you go to this NASA Kepler's website, I have given the link here. You can, there are a lot of other links that you probably will be helpful for you to read and see how they use these techniques to find these exoplanets, right? So there will be a section about exoplanets for you as well in one of these coming lectures, but it will be always helpful for you to go and look at these links and understand and try to learn yourself, right? Right, so that's about the Kepler's laws, and then we come into the era of the Isaac Newton. So he introduced Newton's laws, which you already know. So I'm not going to talk much about Newton's laws. And so there are three laws for the Newton's: first law, second law, and the third law. So assuming that all of you are physics students, I am not going to talk about, explain the Newton's laws, but I have the laws here because Newton laws and Kepler's law, the laws are the fundamental laws that governs, the motions in the planetary system, right? Now, this is just an example how Newton's law uh, is applied in space studies, and this is a rocket that is launched, as you see. Now, the force that discharges the exhaust gases from the rear of the rocket is accompanied by the force that pushes the rocket forward. Now, this is how the Newton's third law works, right? In one example for the application of the Newton's third law in that sense. And then some of the other principles. Now, remember that these are, I am introducing these principles here because we will frequently use these when we need to explain something, right? Newton's third law and in this conservation of angular momentum, especially applied, the motion of the stars and other things. And this is the Newton's law of gravitation, how gravitational law works. And this is also something that you already know, right? So you don't, I think I don't need to explain this for physics students. Anybody have any questions up to here? So I have been, just talking for some time now. So before I move on to the next section, which is the last part of, this set of presentation, anybody have any questions? Anything to tell or anything that you would like to suggest or anything like that? Please feel free to answer or talk, right? So I would like to hear your voices. Right. Right. So let me go into the other section. Now we talked about how planets move around the sky, and so let's look at a little bit on the about the astronauts now, how they move on the sky and how the spacecrafts are, sent to the sky. So it will be important for you to know at least very basic details about these kind of things when you learn about astronomy. Now, the picture that you see here is a set of astronauts in the space. So they are falling freely. So they experience the weightlessness, right? And so I have the names of these as astronomers as here well. But what is important for us is astronomers feel weightless for the same reason that passenger in the elevator whose cables has broken or in an airplane whose engines no longer works feel weightless, right? So this is something that you need to know. So they feel the weightlessness for the same reason. Now, let's say you are in an elevator and suddenly the cables broke down. then you don't feel your own weight, right? So you are, moving with the elevator with the same acceleration, so you don't feel your weight. So that is called weightlessness. And when you are falling, when falling, they are in the free fall and accelerate the same rate as everything around them. So that's what happens under weightlessness. Now, astronauts have the same experience because they don't feel any additional forces. So they feel the weightlessness, right? So they don't feel their own weight. So uh, now, uh, astronauts, let's say the astronauts that are in the International Space Station, they actually falling around Earth, not towards the Earth, right? So when they falling around Earth, this they will continue to fall uh, and are said to be in orbit around the Earth. So they are actually going around the Earth, right? So they are in. We used to tell that they are falling around the Earth, as I have mentioned here. And now, if I go back to the orbital motion and the mass of these planets, there is a connection as well. Now, previously we used the Kepler's third law, and I told you how the orbital period and the length of the semi-major axis is connected in a certain way if you have used certain type of units. But Kepler's laws actually describe the orbits of objects whose motions are described by the Newton's laws of motion. Now, uh, so there is another version of the Kepler's law that is called Newton's formulation. So what has happened is Newton introduces an additional factor of masses for the sun and the planet, both expressed in the units of the sun's mass. And this is the new version that you can see down right here on the this presentation. So this is called Newton's version of the Kepler's law, right? So he introduced the two masses, mass of the sun and mass of the planet. And if both these masses are explained in terms of the sun's mass, so how many, what is the mass of one object? In terms of the solar masses, that is the mass of the sun, right? So that's how you express the masses. The form of the equation will looks like this. So you have a to the power 3 equal. Now the constant will be the masses of the two objects. Now let's say if this is mass and the sun, that will be the mass of the sun and mass of the other planet, right? So that's how it works. However, when you look at uh, and try to compare this particular form, you can see this is a completely different one. Now, a to the cube equal m1 plus m2 times p squared is the Newton's version of the Kepler's law. But what Kepler mentioned was a to the power 3 is proportional to p squared, or when you use proper units, that will be a to the power 3 equal to p squared, right? Now it is the same law. Now we need to understand how these two forms are connected. Now, what actually happens is uh, when you compare the mass of the planet with the mass of the sun, uh, the mass of the planet is very small compared to the mass of the sun, right? So our sun is a huge object with a huge mass. So compared to that, our mass of the mass of the planets are negligible, right? So what has happened was Kepler did not realize that both masses had to be included in the calculation. He did not realize this because depending on the available data and the relationship, that's what he observed at that time. Now, when you look at the masses in the units of the sun's mass, right? So if you get, now we don't use kilograms here, right? So we are using the units of the sun mass. So this is called solar masses. Then the mass of the sun will be 1, right? Because that is the unit. It's like 1 kilogram, right? So if you use the mass of the sun as a unit, then the mass of the sun will be 1, right? So that is 1 unit. Uh, then the mass of a typical planet is negligibly small factor. So that means if you take a mass of a planet, so that will be very small, right? So that means when you have these two numbers, mass of the sun will be very large compared to mass of the planets. And because of that, when we add up the two numbers, you can tell that this will be approximately equal to one solar mass, that is the mass of the sun, right? So the mass of the sun will be equal to one solar mass. And when you add the mass of the sun with the mass of a planet, because the mass of the planet is very small compared to the mass of the sun, you can still get that M1 plus M2 will be approximately equal to one solar mass. By the way, this is very important for you to note here. This symbol means a solar mass, right? So this is a standard symbol and nobody will tell you even in an exam paper if you saw this symbol, so that means it is solar mass, right? Now this makes Newton's formula appears almost the same as the Kepler's. The tiny mass of the planet compared to the sun is the reason that the Kepler did not realize that both masses had to be included in the calculation. So his because of this tiny mass for the planet, he did not realize that it has to be included in the calculation. But even if you included it, because of the mass is smaller, you will get still one solar mass, right? As the answer. Now that is what has happened to Kepler. So make sure that you understand Kepler's third law, and then you know the Newton's form of the Kepler's third law and how these two are connected to each other, right? So understanding all these concepts and remembering Kepler's laws are important for you, right? Right. Now, when you look at the motion of these spacecrafts, uh, the 2 points in any orbit in our solar system has given special names. So that is the place where the planet is closest to the sun and moves fastest is called the perihelion, right? So that is the place where the planet is closest to the sun. Now, as an example, if I go back to Newton's Kepler's second law right here. So this is called perihelion, this point right here where the planet is closest to the sun, right? On the other hand, this point we will call as aphelion, which is the point where the planet is furthest away from the sun, right? So these terms are important for you because this may be the first time that you hear these things, right? Right here, right? So the place where the planet is closest to the sun, move fastest will be perihelion, and then the aphelion is where the planet is furthest away, right? So keep remember these two names, and then for the moon or satellite orbiting Earth, the corresponding terms are perigee and apogee, right? So for the planets, we use two different names, but when it comes to the satellites that we used to have in orbits close to us, we call as perigee and apogee. So these are two different names, but it basically refers to the same positions, right? Now, all the planets have orbits of rather low eccentricity. Even we used to tell that the planets are moving in elliptical orbits, their eccentricity is very small, right? So these are things that you need to have in your mind actually, not the numbers, but the idea, right? Because these are important to explain certain things. And for example, if you take the most eccentric orbit, is the Mercury. Mercury has the highest eccentricity, that is 0.21, right? And all the other planets have smaller eccentricities, that is less than 0.1. And this is the reason sometimes you assume that planets are orbiting in circular orbits. Sometimes people do that. They make this assumption that planets are moving in circular orbits, but it is not actually circular, but most of the planets have very small eccentricities, right? So that means they are very close to circular orbits. So that's how that assumption comes. And there is another thing that is important. The planetary orbits are also confined close to a common plane, which is near the plane of Earth's orbit, which we called as the ecliptic. So basically, all these planets orbit close to a common plane, right? Now, this is why, if you remember that I showed you a path of all these planets, a picture that I showed you, if you look at how these planets move, you will nicely see that they are moving along the same path on the sky, right? So this is a nice observation that you can do if you start observing these planets around from midnight to, let's say, 3 a.m. You will see that the Mars, Jupiter, maybe Saturn, these planets, they will move along the same path on the sky, right? So they basically follow the same path, right? So they just don't randomly go into different positions on the sky. So they from east to west, they kind of follow the same path, right? And even not exactly the same path, roughly it will be the same path. And this path is what we call as ecliptic, right? So that is because their orbits confined to a common plane, right? We call that as the ecliptic. Now, just to give you an idea about these different orbits for different kind of objects that we can see in the solar system, if you consider the planets, the orbits of the planets are actually not that much eccentric, right? So they are nearly circular. If you look at this diagram on the left hand side, the blue color circles, the black color circles represent the orbits of the planets. And you can see clearly that those orbits they are not exactly circular, but very close to circular orbits. And their eccentricity is very small, right? So that is the reason. So they are almost like circular orbits, but not exactly circular, right? And when you look at the blue color ones right here, right? So those blue color ones are actually, so I have mentioned here the details. All these black circles are for the planets Mercury, Venus, Earth, Mars, and Jupiter, right? And the red colors are, you can see the Halley's comet is right here. Like that, these red color orbits are for comets. And for the comets, you can see that they have a very high eccentricity, and some of them are even parabolic paths right here. So their eccentricity is larger, right? So they are generally have the orbits of larger size and greater eccentricity than those of the asteroids. And in blue color, orbits are actually orbits of the asteroids. I think I have mentioned it here. Red are the three comets. So the three colors, red colors are the comets. And for the four largest asteroid series, Vesta and those asteroids are mentioned here in the blue color. You can see that their eccentricity is larger than the planets, but not as large as the comets, right? Now, this is one way of identifying or differentiating planets, comets, and the planets, comets, and asteroids. Right? So there are three different things now. So there are planets, comets, and asteroids, and you can actually get by looking at their eccentricity, you can probably guess. Probably this may be a planet, and this may be a this may be an asteroid, and this may be a comet. Right now, if you know the eccentricity values, you can actually classify these objects. So that will, of course, you have to look at the other properties as well, but this is one important property that you can use, right? Right now, let's look at very briefly like how the motion of the satellites and spacecraft in the space, right? So there are thousands of satellites that you probably know uh, that we place into the orbit around the Earth. Most of these satellites are launched into low Earth orbit since this requires minimum launch energy, right? And we are very concerned about the energy, amount of energy that we use to launch satellites. So most of our satellites are in low Earth orbit. That is because we don't need much energy to push something to the low Earth orbit, right? Now, each year, more than 50 new satellites are launched into the orbit. Spacecrafts have also orbited Moon, Venus, Mars, Jupiter, Saturn, and number of asteroids and comets. And most satellites are launched into the low Earth orbit since, I mean, it's the same thing that I have mentioned earlier. Now, if you look at, if we talk about the satellites and spacecraft, this is the basic information. So there are thousands of satellites now we have placed into orbits around the Earth, and most of them are in the low Earth orbit because you don't need much energy to push something to the low Earth orbit. And can you believe that in each year we normally send around 50 new satellites to the orbit, right? And there are actually a lot of spacecraft that we have uh, orbited around different planets and our own moon. There are spacecrafts, and we have sent spacecrafts to the Venus, Mars, Jupiter, Saturn, and also for number of asteroids and comets as well. Right? So there are spacecrafts orbiting around these objects in the solar system. Right now, to orbit something around the Earth, so there should be a requirement, right? Now, if you look at this particular diagram, just to understand it in a very basic way, if you give a certain speed, it will go a certain distance and come down and will, fall into a position called A. So let's say you increase the speed a little bit more. Let's say you increase speed up to VB, then it will go more distance, but it will go down and fall in some other place, right? However, if we give or provide uh, even a larger speed, initial speed, and if it exceed or if it is a certain amount, then that particular object will not fall into the earth, so it will fall around the earth. So that means it will goes around the earth. Now, this is the basic principle behind, sending any spacecraft or any satellite to the uh, space. So what will happen is for path A, B, the velocity is not enough to prevent the gravity from pulling it bullet back to the earth. In the case C, the velocity allows the bullet to fall completely around the earth, right? So that depends on the initial velocity that you give, right? So there is a minimum velocity that you have to provide for this. Actually, that there is a value for that particular minimum value. And would you like to find it actually for the next? So let me. I was to finish it, but let me stop from here because I would like to talk a little bit more about how these spacecraft and satellites are sent to these different orbits and what is the basic principle behind it. Right. It's a very very small section, so I will take that on the next day and show you how what is the minimum speed required for low Earth orbits and what is the minimum speed that you require to have to send a satellite to the outer space. That means for the other planets, right? So we will have those things described very briefly on the next day. That means the tomorrow morning, and then we will move on to the next section of lectures tomorrow, right? Since we are running out of time today, I'm going to stop the lecture right now. Anybody have any questions? Any questions? Right. So if you do not have questions, let me stop from here. And keep in mind that I will start the lecture from this point tomorrow, and I will try to take another half and 1.5 hour and finish the next section as well, right? So for all others, please let them know. I mean, uh, just to join with the lectures rather than try to listen to these recorded videos. I mean, you will not get the full advantage in that way. And I also do not have any other way of doing this because of the power cuts. I have to move on to the weekends. Let's see whether we can do it in the weekdays on the next week, depending on the power cuts. Other than if not, I will have to move it to the weekend again, right? So that's how it works. Right. So if you do not have any questions, let me stop from here, and I will start the lectures from here from tomorrow 8 a.m. Right. Then thank you everyone for joining. And even after the classes, if you have any questions, what you can do is you can actually post that onto the Google Classroom as a question or in the forum, so that I can answer, and everyone can join to the discussion as well. Uh, or you can just ask, you can even email me, but I would prefer that you post it to the Google Classroom so that everyone can see, everyone can answer, and then we can discuss and find the solution, right? So that will be the better way of doing it, right? Then thank you for everyone, and we will meet again on tomorrow morning. Right? Thank you.